In this video, we're going to look at the idea of model building. And we're going to continue looking at the data set from the 7.1 notes, which was the well switching data. And we're going to look at that data and carefully consider the model building process. But one thing that I really want to stress is when it comes to model building, there really are no explicit rules like you always do this and then this and then this. It really is going to vary, you know, for each data set, for each person. There are different philosophies on how to approach model building. So here we're just going to look at one example. And it's also important to notice that different people could look at the same data and build different models. So hopefully seeing this example is going to be productive as well as instructive. But again, just keep in mind, model building is not a one-size-fits-all. There are definitely different approaches to model building. So just a couple general guidelines. So generally, one can use AIC to judge the quality of a GLM fit to the data, weighted roughly according to the scale discussed in the previous module. Another primary consideration one can use is whether a variable and the sign of its coefficient makes sense. So in other words, before you even see the data, if you thought it would have an important and act in an appropriate direction, are you seeing that when you fit the model? And so for example, if a variable leaves the AIC essentially unchanged, whether to include it or not depends on external considerations. If it makes sense and has a believable direction, leave it in. If not, we might as well remove it. So let's look at this case study of wells in Bangladesh. So again, we're going to consider a data set involving modeling the decisions of households in Bangladesh about whether or not their source of drinking water, or to change their source of drinking water. Many of the wells used for drinking water in Bangladesh and other South Asian countries are contaminated with naturally occurring arsenic and affecting an estimated 100 million people. Arsenic is a cumulative poison with risk of cancer and other diseases thought to be proportional to exposure. So a research team from the United States and Bangladesh measured arsenic levels for all wells in a certain area, labeled the well with its arsenic level, and encouraged households drinking from unsafe wells to switch to a safer well. After a few years, the researchers returned to find out who had switched, and so in this case, switch would be equal to 1, and those who had not switched, switch equal to 0. And so this is going to be our outcome. We will consider which contains information on well switching for 3,200 households, and the data set contains the following explanatory variables. There's the actual arsenic level of the household's well, the distance to the nearest safe well, whether or not members of the household are active in the community organizations, and education. And so this is years of education for the head of the household. So we're going to start out with an exploratory analysis, and this is generally a good first step when it comes to any model building. So whether you're working with GLMs or a different type of model, you pretty much always want to do an exploratory analysis to make sure that you understand the variables that you have. All right, so for the wells data in an exploratory analysis, we find that about 58% of the household switched and 42% of the household had members active in the community. And below are histograms of the other three variables. And so noticing here, if we look at these histograms, just a couple of things we might want to note right off the bat. If we look at arsenic and distance, we see that both of those have a pretty heavy skew to them. And then when we look at education, we can notice, for example, there's a lot of zeros. And then maybe it might make sense if we look at kind of these similar patterns to do some kind of grouping. But we can discuss that later on. And so then it's always useful to compare each variable to the outcome. And so notice here, if we look at switch yes or no compared to community yes and no, we can see here that of those that are in the community, so if we condition on community, we have 708 out of the 1,277 that switched, and then for the no's, we have 1,029 out of the 1,743. So in other words, of those with members in active community, 55% switch, whereas those that without members active in the community, 59% switched. And so then below are side-by-side box plots comparing the other three variables to switched. And we can see here, if we look at arsenic levels, the arsenic appears to be slightly higher for the groups that switched. If we look at education, it appears that education is slightly higher. And then here, if we look at distance, we see that for those that switch, the distance is slightly lower. All of these patterns make sense when we think of what these explanatory variables are compared to the outcome. These are patterns that we would expect to see. So usually a reasonable place to start with models is an additive model. Now, with this being said, the additive model is the most simple model. There are other model building techniques that say start with the most complicated model and work your way down. So here we're just going to start with the additive model. So as always, the regression coefficients have little meaning unless we consider the scale of each variable. So for example, distance is measured in meters, so beta 2 tells us how much the log odds of well switching change if we compare a well 90 meters away versus 91 meters away. That's going to be an inconsequential change. So on the other hand, if distance were measured in kilometers, beta 2 might be enormous. So always keep that in mind, the units that are on the actual variable. Standardization. A reasonable rule is to set changes to be roughly 2 standard deviations. So a reason you might see 2 standard deviations when you work with logistic regression is that a factor of 2 might compare to 0 and 1 variables which have a standard deviation of 0.5. So notice here the range of those variables is from 0 to 1, 2 standard deviations fit in there. That is just a rule of thumb. I've definitely seen standardization where you just use a single standard deviation. So again, this is another one of those things that it isn't always the same. So this amounts to a change of approximately 100 meters, a change of arsenic levels of approximately 2, and a change of education of about 8 years. And so while we're at it, it would be helpful to subtract off the mean of each of these variables. Otherwise, the intercept is essentially meaningless as it corresponds to an arsenic level of 0. So the corresponding R code and output is given below. Again, you can do very similar things to SAS, and we've pretty much seen either in this course or the 681 course how to do these. But so the first thing we're going to do is we're going to start out by just standardizing our variables. So that's what this code is doing here. So you'll notice for both distance, arsenic, and education, we are subtracting off the mean and then dividing by 2 times the standard deviation. And then here we fit the additive model. And then in blue is the output. So one thing to notice here when creating tables or graphs, it's always a good idea to consider a meaningful order. So the following table with variables sorted in terms of importance has a meaningful order. And so notice, one reason that I make this comment here is if we think of the additive model, in terms of when we, what order we put those in R or SAS, doesn't actually matter. It's an additive model. So how we present those results is going to be important. And so that's why, if we, order them in terms of importance, that's going to be more meaningful than just the order that we put them in the model. And so one thing to notice here when we say an order of importance, we are talking about an absolute size. So that's why you see, there's some positive and some negative. But really the important thing here is the distance away from 0, or the absolute size, because if we think about how much impact they're going to have, we're not really talking about whether it's negative or positive yet. It's also useful to compare the adjusted and unadjusted odds ratios. So the corresponding R code and output is given below. So notice when we say unadjusted odds ratios, what we're talking about is whether or not we adjust for the other explanatory variables. So to find the unadjusted, all we do is we fit the model for each of the explanatory variables individually. So first we have switch in arsenic, then we have switch in distance, switch in education, and switch in community. So what this code is doing is it's really just combining all of these into a vector that we can, then look at, and it does that by calling the coefficient function applied to each of the GLMs, and where we're calling the second element. But this looks more complicated than it is. You're really just fitting 4 different models where each of those has a single explanatory variable and pulling out the coefficients. And you can see that down here. Here we have the unadjusted And then the adjusted, where that is coming from, is that's just coming straight from the additive model, where what we've done is we've taken these estimates and then we've taken e to the power of those estimates. And so you can see that here. And so here then is a table comparing those adjusted and those unadjusted odds ratios, and you notice we don't see a big difference there. So our question next might be, do we really need community? And so if we go back up to that additive model, notice that community was the only one that was not significant. And so from here on, let's discard community from the model. There's no statistical justification for it. Not significant, it doesn't improve our AIC, and its negative sign is difficult to interpret, explain. So in short, it adds nothing but clutter to our model. So at this point, it seems reasonable to look at the model using the kind of effect plots you get from BizReg or plots equal effect and proc logistic. So the corresponding R code and output is given below, and similar results can be achieved in SAS. And so then let's look here at these different plots. And I'm going to zoom in just a little bit so we can see this a little bit easier. So you'll notice what we've got here on the y-axis is the probability of switch, and then along the x-axis we have arsenic, distance, and education. So what we can see here is that as the distance increases, we are seeing a decrease in the probability of switching. For arsenic, we can see as arsenic increases, we also see the probability of switching increases. And then for education, we see that as education increases, so does the probability of switching, but we notice that this one, that increase isn't as sharp as it would be for, let's say, distance or arsenic. So let's investigate next some of our assumptions. So the main assumptions that our model is making at this point are the following. There are no other unmeasured covariates that affect the probability of switching. The effect of each variable is linear, and no interactions. So the first assumption is probably not true, but there's really nothing we can do about it after the data has been collected. The second and third assumption, however, we can investigate. So one thing that we might want to consider are some transformation. So given that we had a highly skewed distribution for distance and arsenic that we saw at the beginning, a log transformation would seem reasonable. And for education, the bar plot we looked at earlier would suggest the following education categories. And we looked at this just a bit. We noticed that there were a lot of zeros. We noticed that we kind of had this grouping here that looked like this from 1 to 5. We saw something very similar from 6 to 10. And then we might want to group the last grouping together. Now, one thing to talk about with groupings is, your bar plots might show some kind of natural grouping that would make sense, but at the same time, you don't want to have your categories be wildly different in terms of width. And so notice here, when we look at the low and the medium, those have the same width. And then our end ones kind of by themselves make up for that last grouping. And really, even if we look at higher education greater than 11, if we look at the highest value we have in here on the chart, that is 16, so that's really about the same width. Now with 0 obviously is just a single value, but we notice here that we have a very high bar for the 0, so it makes sense, especially for it being at the very end of the range, and given how many observations we have in the 0 category, for it to be its own category. And also, if we think about that in terms of education, 0 has a very specific meaning. I mean, you had no education whatsoever. So it makes sense for this variable, for 0 to be by itself. And there are other variables that you will see that as well. Now, unlike linear regression, it's difficult to sense an appropriate transformation in logistic regression by looking at the residuals, but we can try fitting these models just to see what happens with the AIC. And so below, with the corresponding AICs, here's what we have in R with the output. And then here we have the results in a table. So this is fairly convincing evidence that we should adopt the log arsenic and education category transformations, but stick with the linear effect of distance. And so notice that this model has an AIC of 3,878 as seen below. Right, so again, it seems reasonable to look at the model using those effect plots. And so note that the effect of the log transformation compared with the earlier model, the probability of switching changes more rapidly for low arsenic levels but is flatter for higher. This implies that people react more strongly to the difference between arsenic levels of 1 and 2 than they do for 5 and 6, which seems pretty reasonable. For education, our new model indicates that there is little difference between individuals with none or little education, but higher levels of education are associated with increased probability of switching again. This seems reasonable. So finally, the last thing we may want to consider for our model would be interactions. So in this example, where we only have 3 variables, we might as well just consider all two-way interactions. If we have more terms, we would have to narrow our focus. So typically this would include concentrating on interactions that involve the most important main effects, concentrating on interactions involving the primary treatment or exposure if there is one. Now, and the other thing to think about here is, I didn't say anything about the three-way interaction. Once we get past two-way interactions, you rarely are going to see three-way interactions, four-way interactions, these really high interactions in models. Most of the time, you're going to see main effects in two-way interactions. The corresponding R code and output is given starting on the next page. Well, I should say on this page. Similar results can be achieved in SAS. So here is that output, again, where we've included the interactions. There are the AICs. And so the results for the transform version of the variables are given here. So it seems that we've got pretty strong evidence that the effect of distance is not the same for all levels of education, and that other interactions really don't seem to add that much. So the coefficients for the interaction model are given here in this table. And so one thing to note is that arsenic and distance have been centered, and a 1 unit change in each corresponds to approximately a 2 standard deviation difference. So this is one thing you always want to keep in mind if you are standardizing. Remember, that is going to change your interpretation. So based on this table, we can see that the distance has a large effect for low education households, a moderate effect for medium education households, and seemingly no effect for high education households. So presumably this is due not so much to education per se, but because education serves as a marker for socioeconomic status. Thus, while individuals with low education are presumably poorer and must walk to the next well, better educated individuals are more likely to be wealthy and able to afford other less onerous means of transportation. So as a last note here, we need to talk about communicating models with interactions. When communicating the results of a model with interactions, reporting regression coefficients directly is really a good idea. Only a small fraction of your audience is going to be able to discern their meaning. So instead, it's better to report separate odds ratios for each level of the interacting variable, or to provide plots indicating the relationship at each level. So for example, if we wanted to look at a plot of distance at each level of education, we could do something like the following. And so notice here, each of these plots represents a different education grouping, and then for each of these we can look at the effect of distance on the probability of switching. And so we can see here that for those low education groupings, we see a dramatic drop in the probability of switching as we increase distance. But for the higher education groups, we see less of that effect, and even when we look here, this one becomes almost flat. Here's just an alternative plot of distance for each level of education. So here we could put them on a single plot where we have a line for each of the levels of education. So in summary, it's important to keep in mind that model building is an iterative process and that no model is ever going to be perfect. And so below we have the process in terms of the AIC. And so we started out with the null model. We have the basic additive model. Here we've removed community, we've had the transformations, and then finally interactions. And so here we can see how the AIC is changing and that we are progressively getting the AIC to be lower and lower.